Problem number 16. A child of mass m holds onto the end of a massless rope of length L, which is attached to a pivot at height h above the ground. The child is released from rest when the rope is straight and horizontal. At some point, the child lets go of the rope, flies through the air, and lands on the ground a horizontal distance d from the pivot. On Earth, the maximum possible value of d is dE. If the setup is moved to the Moon, which has 1/6 the gravitational acceleration, what is the new maximum possible value of d? Solution to problem number 16. This problem is most easily solved using dimensional analysis. D must be some function of L, H, M, and G. Of these, G is the only value that contains seconds. Since D does not contain seconds, distance cannot depend on the value of G, thus, the correct answer is C. This is the solution to problem number 16. Problem number 17. Consider the following system of massless and frictionless pulleys, ropes, and springs. Initially, a block of mass m is attached to the end of a rope, and the system is in equilibrium. Next, the block is doubled in mass, and the system is allowed to come to equilibrium again. During the transition between these equilibria, how far does the end of the rope, where the block is suspended, move? Solution to problem number 17. When the block is doubled in mass, it increases the tension in the bottom string by mg, so the third spring's length increases by delta x3 equals to mg over 3k. Since the bottom pulley has two ropes pulling down on it, the downward force on it increases by 2 mg, which means the upward force on the top pulley also has to increase by 2 mg, so the tension in the top string also increases by mg. Then the first and second springs increases in length by delta x1 equals mg over k and delta x2 equals mg over 2k. Finally, by considering how changes in length of each spring affect the position of the mass, we conclude total delta x equals sum of all three enlargements, which is 11 mg over 6k. This is answer E, and this is the solution to problem number 17. Problem number 18. A satellite is initially in a circular orbit of radius r around a planet of mass m. It fires its rockets to instantaneously increase its speed by delta v, keeping the direction of its velocity the same, so that it enters an elliptical orbit whose maximum distance from the planet is 2r. What is the value of delta v? Hint: when the satellite is in an elliptical orbit with semi-major axis A, its total energy per unit mass is negative gm over 2a. Solution to problem number 18. The initial speed in the circular orbit is v initial equals square root from gm over r. In the elliptical orbit, the semi-major axis is a equals 3r over 2, so the total energy per satellite mass is negative gm over 3r equal negative gm over r plus 1/2 v final square, which implies v final square equal 4 over 3 mg over r. So from here we have v final minus v initial equal answer B. This is the solution to problem number 18. Problem number 19. A wheel of radius r has a thin rim and 4 spokes, each of which have uniform density. The entire rim has mass m, 3 of the spokes each have mass m, and the 4th spoke has mass 3m. The wheel is suspended on a horizontal frictionless axle passing through its center. If the wheel is slightly rotated from its equilibrium position, what is the angular frequency of small oscillations? Solution to problem number 19. This system is a physical pendulum. The moment of inertia about the center is in expression 1, when the system is rotated a small angle theta from equilibrium. The restoring torque comes from the difference in masses of the top and bottom spokes in expression 2. So we have equation number 3 for rotational motion. As a result, we have expression 4 from which we read off omega equals square root from g over 3r. Which is answer A. This was the solution to problem number 19. Problem number 20. Four massless rigid rods are connected into a quadrilateral by 4 hinges. The hinges have mass m, and allow the rods to freely rotate. A spring of spring constant K is connected across each of the diagonals, so that the springs are at their relaxed length when the rods form a square. Assume the springs do not interfere with each other. If the square is slightly compressed along one of its diagonals, its shape will oscillate over time. What is the period of these oscillations? Solution to problem number 20. Suppose that one of the masses has moved by amplitude a from its original position, and it currently has speed 0. By symmetry, all of these masses have maximum speed v maximum in equilibrium position when displacement is 0. So, the total maximum kinetic energy of all 4 masses equal to total potential energy of springs, and we have equation 1. From this equation we have v maximum equals square root from 2k over m multiplied by amplitude a. But from other hand for the harmonic oscillation we have expression v maximum equal omega multiplied by amplitude, so finally omega equals square root from 2k over m and period t equal 2 pi multiplied by square root from m over 2k. That was answer B, and this was the solution to problem number 20.